conventional or basic forced air heating systems. In this presentation, we're going to look at how the capacity of such a system is measured, what the basic types are, what the components inside a forced air system are, what the basic sequence of operation is, and some of the common problems that electricians may encounter when working with a forced air heating system. Heating capacity is measured in BTUs, or British thermal units of heat energy, which can be produced by the equipment. 1 BTU is equivalent to the amount of energy required to heat 1 pound of water by 1 degree Fahrenheit. Forced air heating systems are categorized by the source of heat that is used in order to power the assembly. Natural gas, propane, heating oil, and electric are commonly seen in the residential, commercial, and industrial sectors. Also, the air direction, the direction that the air is forced, is another means of categorizing this type of furnace. Let's start by looking at sources of heat. Combustible fuel, like natural gas, propane, and heating oil, will use something called a heat exchanger. The heat exchanger is an enclosed metal tube or chamber that the flame allows the combustion gases to flow inside. It is completely separate from the building air, which then comes into contact with the surface of the heat exchanger, and heat is then transferred to the air and it moves further into the building. Typically, for this type of heating system, we only need a 15 amp circuit. The heat exchanger always prevents the mixing of combustion and building air. Here's another example of what a heat exchanger does, and we can clearly see the difference in the building air or the house air and the combustion air, which is inside a separate chamber connected to where the burner is and the burning gas. Here are two different types of heat exchangers, and you can see clearly that there is no connection between the air that would be inside this little tube here, or the tube on this side, and the air that would then move across it. A heat exchanger is the main item inside a combustible fuel furnace, and it takes up the majority of the space. An electric furnace, by contrast, is slightly different. It's still forcing air through the building and heating it, but in this case, we're using electric heating elements. Because of this, there is no heat exchanger. Instead, we are simply blowing air past live electrical heating elements like a toaster. Usually, the circuit requirements for such an item are around the 100 amp range, and usually a residential service will need to be at least 200 amps in order to accommodate an electric furnace. The heating elements are typically in trays or stages, and a heating relay may control which ones are turned on for any amount of heat required. And this is a picture of a replacement electric heating element for a standard electric furnace. Upflow furnaces are ones where the air that is heated is blown in an upward direction and then off to the building through the hot air registers. This would typically be located in a basement. A downflow furnace is used commonly for modular and trailers type of homes because the heated air is blown down underneath the floor and then up through the heat registers in the rooms. A horizontal flow furnace is often installed in a small attic space or a crawl space, and the air is blown horizontally underneath the floor or above the floor to the heat registers. A warehouse heater has a directional louver, which we can then position by hand when first installed to determine the direction of the airflow. Basic components. The most basic component that we're going to have in a basic gas-fired forced air system is a gas valve. The gas valve is one where the coil is energized and the plunger moves in an upward direction and allows gas to flow through the orifice or valve seat. There are larger types of gas valves used in heating applications known as diaphragm gas valves, and these utilize our understanding of pressure differential. In a situation like this, the plunger itself is not actually moving the main orifice. The diaphragm here is a flexible rubber plate or rubber membrane that connects to a rigid plug. If the pressure above and below the plug are equivalent, then the plug remains in its downward position and no gas flows. If the plunger is raised, what will happen is the pressure will be bled through the gas bleed port out from above the diaphragm, causing a lower pressure above the diaphragm. This then allows for the main gas pressure in a low gas pressure system around the 2 to 3 psi to push the diaphragm plug up, and gas then flows off to the heating assembly. Bimetallic strips are heat-activated switches, which are used in many different types of heating applications for control. They bend or twist when applied to heat, and when heat is applied to them, we can connect these to different types of electrical circuits to either open or close contacts. A spiral connected bimetallic strip will turn a dial and rotate as it heats. These are commonly used in a slightly different form in thermostats and different types of thermometers. In a basic gas-fired system, a spiral bimetallic element is utilized to activate two different switches. The assembly looks like this, and it's commonly used in larger commercial apparatus as well as older residential furnaces. This device is called a fan/high limit switch. A basic gas-fired heating system will utilize a schematic like this. The schematic is a very universal type of control sequence that most basic heating systems will use. It's good practice to sketch this schematic down just to have a basic idea as to what the sequence will be of operation. Keep in mind, as soon as we move into HVAC territory, that a large portion of the control will be mechanical in nature and not electrical. And this can lead to confusion as people do not see the mechanical interaction on the electrical schematic. On this schematic, we see that there is a fan control switch. The fan control is a normally open temperature switch, and it controls this, the main blower fan, which will blow warm air throughout the building. Below it, we see that there is a high limit switch. It is a normally closed switch, and it controls simply a transformer. Notice they are both inside a dotted line box, which means that they are both part of the same object. Both of these are connected into the fan high limit control switch. The thermostat is located in the lower voltage section of the schematic, and it controls only the main gas valve. The reason for the transformer is that the main gas valve operates at 24 volts, and the 120 provides the power for the 24-volt circuit. The thermostat is located in the room that we want to have heating. The fan control and high limit is located near the heat exchanger in the furnace itself. And when we take a closer look at this item, we will notice that there are three separate settings on it that can be adjusted by the user. There is a high limit setting. This is the highest setting on the unit. This will open a normally closed contact when the temperature is reached. 200 Fahrenheit, they're showing as the typical high end. What this will do is turn off the furnace when we have an abnormally hot condition inside the furnace itself. The other two settings are fan on and fan off. The fan on setting refers to the main blower fan that is going to push warm air throughout the building. The fan on setting is going to be slightly higher than the fan off setting. And so what we're doing with these two settings is ensuring that the fan will turn on when the air is adequately warm and the fan will turn off before the air inside the furnace gets too cold. We don't want cold air blown through the building. So how does this entire system function? Well, first let's close the disconnect, which is just providing 120 volts to our system. At this point, we have no need for heat, and we know this because the thermostat is in the open position. Remember, the thermostat will close when the temperature drops. At this point, the room cools below the desired set point of the thermostat. The thermostat closes the circuit to the main gas valve, and in doing so, the gas valve energizes, physically opens, and the gas burner ignites. Now, as soon as the gas burner ignites, the furnace plenum, or heat exchanger, will start to increase in heat. Notice that the main blower motor has not turned on, and that's because at this moment, the temperature would be too cool, and we would be blowing cold air throughout the building. Eventually, we reach the fan on heat setting in the fan control switch. This then closes the circuit to the main blower fan, and this causes the blower fan to energize and start blowing heated air throughout the building. The room slowly heats, and eventually the thermostat recognizes this rise in temperature to the desired room temperature. The thermostat then opens, de-energizing the main gas valve. Notice at this point that the main blower motor is still blowing hot air, and that's because the heat exchanger is still hot. The gas valve is de-energized, it has physically closed, and the main burner has extinguished. The fan will continue to run until the heat exchanger cools to a point where we reach the fan off setting. At this point, the fan off switch opens and the main blower motor turns off. We have now completed an entire heating cycle and we're ready for another once the room temperature cools. Another way to present this information would be to show the relative temperature settings for our three different items on our fan high limit control assembly. In orange is shown the furnace plenum temperature. When the burner first starts, the temperature inside the plenum increases. And remember, this has been initiated by the thermostat closing. As the temperature increases, we finally reach the point of fan on. The fan turns on and air is blown past the heat exchanger. What this causes is a reduction in temperature because we are now wicking heat away from the heat exchanger, and it will hang out at this level here until eventually the thermostat tells the burner to stop or de-energize because we've reached the desired room temperature. At this point, the fan continues to run until the temperature in the plenum drops down to the fan off temperature, at which point the fan stops. At this point, we're again ready to continue on another burner or heating cycle. What happens when the high limit operates? Well, the high limit, its entire purpose is to provide power for the 120 volt transformer. On the other side of the transformer, the 24 volt side, its entire purpose is to supply energy to the main gas valve. So if we were to look at this system and energize the main gas valve, and physically opens and the gas burner ignites because the room is cool and the thermostat is closed, the heat inside the heat exchanger should rise, and eventually we should reach the fan on setting. The switch will close, but what happens when there's a problem? What if the fan switch is broken, or there's a broken wire, or the fan blower motor itself is damaged? Well, in a situation like this, the temperature inside the heat exchanger will continue to rise because there is no air movement past it. And at a certain point, we're going to reach a situation where we're getting to hazardous levels and could lead to a fire. In this situation, the high limit should open once we reach that predetermined high level temperature. And in opening, it should de-energize the transformer which de-energizes the 24-volt section of the schematic, which in turn de-energizes the main gas valve. Once the main gas valve de-energizes, it closes and the flame is extinguished. Now, will the heating system remain off? And the answer is no, it won't. Because once the plenum cools, the high limit switch will go back to its normal position, which was in the closed state. So as the plenum cools, eventually the high limit will close, which will again initiate the start of a heating cycle. But since we still have a damaged portion to the blower motor control circuit, we're going to again end up having a high limit operation. And so this is referred to as high limit cycling. The room never receives heat, and it's a telltale sign that there's a problem with the air being blown past the heat exchanger. Perhaps it's blocked, and there's no possible chance for air to move past it. Perhaps the motor itself is damaged. Perhaps the switch is damaged. Perhaps the wire that connects the switch to the motor is damaged. Whatever the case, high limit cycling would be seen by an individual as the burner starting, reaching a high temperature, and then turning off. Turning back on, high temperature, turning back off, turning on, turning off, turning on, turning off. But at no point is the main blower turning on. Now, how does the main burner ignite? This is something that we have skipped over in this presentation. We obviously are not going to use a match every single time we go to light the main burner. It would be somewhat ridiculous. Instead, we're going to add a final section to our basic heating schematic, which is used universally across most portions or sectors of the electrical industry. We now have three different voltages, 120, 24, and all the way down here, 26 to 32 volts DC, or 26 to 32 millivolts DC. And in that range of voltage, we should know that a thermocouple will be used because a thermocouple is an energy generating device that is capable of generating a voltage around the range of 20 to 35 millivolts. We'll take a look at this in more depth in the next presentation when we look at how the burner is ignited automatically by the main furnace.